Okay, so I'm pleased to introduce Adele Moncuquet from West. Thank you very much, Adele.
Thank you for the introduction. So thank you for letting me presenting my part of my results on in situ observations of nonlinear internal waves with trapped core in the south coast of the Bay of Biscay. So I'm a PhD student, and my awesome supervisor, which is really cool to work with, are François Dufoy, Florent Grasso, and Pascal Lazure from IFREMER, Nicole Jones from UWA Oceans Institute, and Lucie Bordois from the CHUM. So first, about the motivation for this work is, it's a double motivation. First, the Bay of Biscay is known as a hotspot for internal waves generation for a long time. However, there is no studies of coastal internal waves over the Bay of Biscay. So all the studies that have been conducted up to now consider internal waves in water depths higher than 200 meters. So in less than 200 meters, there are no studies. On the other hand, nonlinear internal waves can resuspend sediment, as shown and observed, and nonlinear internal waves with trapped core can be an effective transport mechanism. However, internal waves effects are not taken into account in the sediment budget in the Bay of Biscay. So this is a non-exhaustive list of authors. I'm sorry, I don't have time to go into more detail, but if anyone is interested, we can talk about it. So our site of interest is in the south of the Bay of Biscay, called the Aquitaine Shelf. On this part, so here the barotropic tide is mostly semi-diurnal tide, and compared to the rest of the western French coast, the tidal current is weak. So I work with six moorings. 3 are in 60-meter depth, and the other 3 are in 160-meter depth. And when you put them, and you see that they are separated by a shallow slope. So as I said, I use measurements from an oceanographic campaign called Étoile, which has been conducted for 1 month in July 2017, and which is composed of temperature and pressure sensors and current profiler with high frequency measurements. So we can have temperature, pressure, velocity, 3-dimensional velocity, and backscatter, which is the equivalent for suspended material. So I will just focus on the measurements made in 60-meter depth. So we are at a fixed point, and we use the temperature and pressure measurements at different water depth. You can see here a red point with points which correspond to the average height of the sensors. And so at a fixed point, we're looking at the variation of temperature, and what we see is quite interesting, because we see 3 different time scales. First, there is cold water coming from the north, so the width of the deep layer is increasing with time, and the width is bigger for the northern coast in 1C. It's a bit thinner in 2C, and it's even thinner in 3C. The second time scale is the internal tide. So there is isotherm oscillation with a frequency equals to the semi-diurnal tide. And the amplitude of the internal tide is around 15 meters, which in 60-meter depth is not so small. And so the internal tide is becoming nonlinear here. And the last time scale that we can just guess by looking at it is the timescale of nonlinear internal waves. So what we call here nonlinear internal waves. And what do I call nonlinear internal waves? Well, you saw a lot of really cool presentation of about solitary waves and stuff. So what I call nonlinear internal waves are also sometimes called solitary waves or solitons. Okay. So what we search is high frequency isotherm excursion. So when I say high frequency, it's below 20 meters and 20 minutes, sorry. And in this window of 20 minutes, we also look for vertical velocity inversion. To be nonlinear, the isotherm excursion must be of high amplitude compared to the stratification width. So I set a criteria for which I say, okay, if the isotherm excursion amplitude is higher than 10% of here the total depth, then we are looking at nonlinear internal waves. And here we see a graphic with the vertical velocity and isotherms for 3 hours, and we see nonlinear internal waves of 2 polarities. The first one is one of depression, where the isotherm excursion is going downward and the amplitude is so negative, and isotherm of elevation, where the excursion is going upward, and so the amplitude of the excursion is positive. So this will be of great importance because when looking at the effect of the low dynamics on the high frequency dynamics. So I said earlier that we see cold water arriving from the north, and this is going to change the stratification. So this is what we show here. We take all of our isotherm signals and we put them in a 36-hour low-pass filter, just to look at the low dynamics, what is happening. And so we see the cold water front, and thanks to these measurements and knowing that in this location the salinity is not varying with depth, we are able to compute the Brunn-Väisälä frequency, which is a measurement for the stratification. And what we see in the low dynamics for the background stratification is, at first, there is a picnoc line close to the seafloor and weak stratification at mid-depth. The stratification is stronger at the surface. Then the picnoc line is rise up because higher up in the water column, the stratification at mid-depth is still weak, and we have the picnoc line, so the maximum stratification at the closer to the surface. And then the picnoc line is close to the surface, the stratification at mid-depth increase, and there is low, so really weak stratification close to the seafloor. So how this is going to change the high frequency dynamics? To answer this question, we take 2 isotherms. One isotherm of 16 degrees to look at what is happening close to the seafloor, and one isotherm of 19 degrees to look at what happens more close to the surface. We take those isotherm excursion and we put them in a high pass filter with a cutting frequency of 2 hours. So now we just have excursion of high frequency, and what those excursions are higher than the limiting amplitude, we say, okay, so this is nonlinear internal waves. And what we see for the high frequency dynamics is that the red curve, the isotherm of 19 degrees give us the information of surface nonlinear internal waves, and we see surface nonlinear internal waves all the time, except during the nip tide, when the internal tide is not energetic enough. And we see also deep nonlinear internal waves, so nonlinear internal wave close to the seafloor, but we only see them at the beginning of the time series, and we only see them when the internal tide amplitude is high enough, so not during the nip tide, and when the picnoc line is close to the seafloor. So here to say that we observe different nonlinear internal waves depending on the stratification profile. So now let's focus on one specific train during the first period. So we are when the stratification profile given okay, my cursor here given on the left graph at the bottom. So the stratification is maximum at depth, minimal at mid depth, and goes high up close to the seafloor, close to the surface. Sorry. Okay, and what we see is 6 elevation waves and one depression waves. Looking at the horizontal onshore-offshore current, which is the first panel, we see that all of them are going offshore, onshore. So the elevation waves and the depression waves. We see that they are not interacting, and we all, thanks to the vertical current, and we also see that all of these nonlinear internal waves have a backscatter signature. So backscatter is a way to look at suspended materials. So, okay, all of them have an effect on the surrounding materials. And something one can notice, which is, yeah, okay, it's that in the same train, we observe depression and elevation nonlinear internal waves. If now we focus only on one solitary wave, so one nonlinear internal wave, and we go inside his frame. To do so, we start by measuring the propagation speed and the direction of the wave. To do so, we use the method described by Scotty et al. In 2005, which uses the backscatter measurements time lag between the different beams of the current profiler. Once we have the propagation speed and direction, first we can define the coordinate in the wave frame that is defined here. Then we have the direction of the wave, so we can compute the current in the wave direction. So in the right graph, what I show is streamlines of the current in the wave direction and superpose over the backscatter measurements. What this graph tells us is that there is 2 regions here, 2 flow regions. First, a region where the streamlines are quite regular. The rotational part of the flow is negligible. So we can say that the flow is potential. And knowing that the backscatter is a way to look at resuspended materials, we see that in this flow region, the material follows the streamline. And this tells us that the potential flow is stationary in the nonlinear internal wave frame. That's for the first, flow region. The second flow region is completely different. It's inside the nonlinear internal waves and show recirculation and show a rotational part of the flow way stronger than the other. So when we see this, the rotational core is likely to be trapped. But another way to look at this is to look at a kind of Froude number. So now if I compare the current in the wave direction with the propagation speed of the wave, I'm able to say if my wave capture or not matters. So if the current in the wave propagation is in the same direction, and if it's higher than the phase speed, the Froude number is above 1, and then the wave may capture material. However, when the current in the wave direction is on the other sense, so in okay, so it's minus value of Froude, or if the current is weaker than the phase propagation, then the Froude number is below 1, and it's likely that there is no capture. Here, we look at 2 different nonlinear internal waves in the train that I showed you, S6 and S7. We see that the Froude is above 1 in each of the nonlinear internal wave score. So in the first stratification regime, elevation waves transport trapped core. So in conclusion, we observe a stratification profile varies in time and change the type of nonlinear internal waves observed on the coast. The nonlinear internal wave of elevation are only observed when the pycnocline is close to the bottom and the mid-depth stratification is weak. And the nonlinear internal waves of both polarity contain trapped core and are observed at each tidal cycle for a weak stratification at mid-depth and higher stratification at the bottom and close to the surface. And what I showed you is also true for the two other sites, 1C and 3C, because, okay, I didn't say this, sorry, but I only focus on white side. Thank you.
Thank you very much, Adele. So are there any questions? So what do you intend to do in the future for the remaining of your PhD? You would like to, you will obtain new data elsewhere?
Yes, okay, so because there is other data, because in this we don't have any sediment measurement, so we can't say if the backscatter is related to sediments or biological materials. And we started also to make a daylight simulation of this situation. So yeah, in the future, look at the situation in an idealized numerics, and I hope to be able to look at turbulence measurements with Nicole Jones, which is a which use turbulence measurements.
I was expecting a question from Magda. Go ahead, Magda.
Thank you, Adele. That was a really interesting talk. Beautiful observations you have. I was wondering if you could tell me a bit more about the topography in that region in terms of the slope and the shoaling, and also if you know what ultimately happens to these waves.
Okay, yeah. Thank you, Magda. By the way, I really enjoyed your presentation and thank you for the question. Okay, so here the slope is weak, and in fact, when I compute the Erie-Barren number based on the internal tide, what I found is that the Erie-Barren number is really low. And so I expect those deep nonlinear internal waves coming from a degeneration of the internal tide due to weak slope effect.
That's great.
So,
thank you.
Thank you.
Okay, another last question. You have one in a chat. Can you read it in a chat?
Okay, yeah. Did you find that nonlinear internal waves can modify the background stratification? Okay, that's a complicated question because it's about time scale. So what I saw is that the nonlinear internal waves, when they pass, move upward or downward if it's for depression waves, the pycnocline. So for instance, for the elevation waves, the pycnocline is pushed upward. But yeah, that's all. About mixing, I did not look at the mixing part and this kind of stuff.
Okay, thank you for your answer, Adele. If there is no other questions, thank you very much, Adele, and we will move to the next talk by Noé.